everyone. Before we go through our overview for Unit 5, I think that it's really important that we take a minute just to verify that we feel really good about what a sampling distribution is, where it comes from, how it works. So in today's module, you have two separate things to work on. The first one is this printout of a bunch of different graphs, a bunch of different data. And on this printout, we are going to go over what exactly is a sampling distribution. Then your other paper is the actual overview. Your other paper, is the actual overview of Unit 5. You are going to turn this paper in. You are turning in your overview. You do not need to turn this in. You will also be turning in this review. So the intention is we're going to go over the foundation of this entire unit, and then you should fill out your overview. Hopefully the two of these things will be most of what you need to complete this review packet. So, turning in these two things. This, I think, is essential understanding to this unit, and it is, I believe you will do better on the exam if you understand the ideas that we go through on this paper. So to begin the analysis of these graphs, I just want to revisit where we started in this unit. So we started by talking about how we often want to know things about a population. There's an issue with that, though, because gathering information from a population is often too costly or too timely to actually do that. In some cases, we can't do it. So the next best thing is taking a sample. What are some of the things that we might want to know about a population that we can estimate with a sample? Well, the two most common things are an average or a proportion. In fact, these two things are so common, they have their own symbol. An example of an average would be the average income of college graduates. An example of a proportion would be the percent of or the proportion of recent high school graduates that will join the military. But those are not the only two things that we might want to know about a population. For instance, we might want to know the range of money spent at a gas station. So to me, I do think that this would be interesting. Probably not earth-shattering, but I would be interested to know what is the range of money spent at a gas station, because you have people who will go in and buy a candy bar, or 3 if you're me, and then you have people on the complete other end who are there to fill up their RV with gas and all the toys and forerunners that you are going to use with your RV and your big old truck that pulls the RV. So it would be interesting to me to see what the range is between the smallest purchase, like a candy bar, and the largest purchase, which I'm guessing is probably filling up gasoline for like a diesel or an RV or a truck. So I think that that would be interesting information to find. We might also be interested in the maximum utility bill in a neighborhood. Maybe we want to buy a new house. Maybe your parents want to buy a new house because they have so much equity in their current house. So you're looking to buy a newer, better, bigger house. But with a newer, better, bigger house, sometimes utilities are more expensive. So you might want to know, well, what's the maximum amount somebody has had to pay in this neighborhood? Another one may be the median age women have their first child. So like many real life distributions, I would imagine that this distribution is skewed right. I bet you most people have their kids between 20 and 30, and then there are probably some outliers toward 45 and 50. So we probably wouldn't want to know the average age at which women have their first child, because we probably have high outliers and in some cases maybe even low outliers. So instead of using the average, we would want to know the median. So we have a population. We want to estimate things about our population, and in order to do that, we'll take a sample. What might we want to know or estimate with our sample? Most common, average, and proportion. But that doesn't mean that these things are not also things that we're interested in. So our first example has to do with an average, and it is data that we have seen before. So this is the number of pairs of shoes owned data from the beginning of the year. What I have graphed here is the number of pairs of shoes owned, and my population is 68 AP students. So capital N is 68 AP students. This distribution is right skewed, as you can see. But for this one, maybe we want to estimate the average pairs of shoes AP students own. So I know the average from when we did this problem. The true average of this population is 15.4. So this is a population distribution, and in this case, our population is actually very small. Our population is only 68 students. The average number of shoes owned by these students is 15.4. So what I did was took all 68 students, added up their number of shoes, divided by 68. We would typically not take a sample from these students because this population size is manageable. But when we want to talk about sampling distributions, we have to do a manageable population so that we can show you what a sampling distribution really is. So, population 68 students, true mu is 15.4. Let's say for some reason we didn't know that the true mu was 15.4. So we're going to take a sample of these 68 students to estimate what true mu might be. So we're taking 10 students from these 68 students. So our first sample, or a sample from these students, may look like this. So notice this is a sample distribution. This is one sample of 10 students. This is one sample of 10 students, and these 10 students come from this group. Because this is a histogram, we can't calculate the average, so I will just give you the average. The average of these 10 students was 18.1 pairs of shoes. So my estimate for the population would be 18.1. My estimate is that the average pairs of shoes owned for these 68 kids is 18. It's really important that we understand that this is the sample average, which we also often refer to as the sample mean. Well, maybe we want to take another sample of 10 students. So we have a sample here and a sample here. So these samples, these three separate samples, come from this population. And they're each different samples. They have different set of 10 kids. This sample average is 16.7. So if this were the only sample that I took, my estimate for the average pairs of shoes these kids own is about 16.7. This one gives me an estimate of 13.2. So key thing to note at this point is this is a population distribution. It has a true average of 15. We could take samples from this population to estimate this value if we didn't know it. So we have a sample here, one sample distribution with a mean of 18.1. And here we have a sample distribution where the mean was 16.7, and a third sample distribution where the mean was 13.2. I'm sure you guys are noticing that each sample has a different value. It's important to note here that X bar is different, which is the same thing as varies, because of sampling variability. And remember, sampling variability is natural and okay. It's natural and okay that our samples have different averages, because our samples have a different set of 10 kids in each sample. So of course the values are going to be different. But what we know is, if we take all the possible samples of size 10 that we can from this population and we graphed it, we know that those samples will be clustered around the true value of the population. So this sample is a little high, this sample is high, this sample is low, but when we take all possible samples and plot them on a dot plot together, what we end up seeing is a sampling distribution that is centered, or the data is clustered around this true value. So the first thing that I want to do in looking at this sampling distribution is make sure that it is clear that we all understand that you can find these three samples in this sampling distribution. So I'm going to highlight these. I'm going to give them each their own color, and then I am going to transfer the points to the graph below. So I'm giving each of these sample values its own color. Sorry, I'm just being a little bit picky about the colors I want to use. And now I'm going to come down here and show you where they would be on this sampling distribution. Now, there are so many samples here. There are thousands and thousands of samples in this sampling distribution, so you can't even tell anymore that this is really a dot plot. There's just so many dots here that you can't distinguish them. So what I'm going to do is I'm going to draw my dot really big so that I can see where my dot might go. So for this 18.1, I'm going to come over here to where about 18.1 would be, and I'm going to draw a huge dot. And then I'm going to fill it in with this blue color. Then I'm going to do the same for 16.7. And he doesn't have to be toward the x-axis. Like 16.7, that particular sample might be right here. And then lastly, my 13.2 would be somewhere around here. Oh, wrong color. So what I'm trying to illustrate here is that these three sample values that I got would then be, or could then be, placed on the sampling distribution. So a few things to note about the sampling distribution. Number one, this is all possible samples of size 10 from the 68 students above. So all of these samples of size 10 came from these 68 students. Why do we investigate? Well, we investigate this because it turns out that if we plotted all of these samples, the center or the mean of this distribution is equal to true mu. So true mu is 15.4. And if I highlight that area on this distribution, we can see that the data is clustered around about 15.4. So what I'm going to write down here is that, I'm going to make that a little bit longer. We can use the median to estimate the average sample value. Remember, this thing means average sample value, which means the same thing as the mean of our samples. Well, why are we using median to estimate this? Well, otherwise we would have to add up thousands of numbers and then divide by the however many samples we were able to take. That's just not realistic. So it's easier to say, okay, where's the center of this distribution? Because I know that median will be about the same as the mean. So here I'm going to make a note, use median to estimate mu sub x bar, because finding median is faster and easier. So we are using the median to estimate our average sample value because it's faster and easier than adding up thousands of sample values and dividing. So now let's just take an overall look and make sure that we understand what is happening here. This is a population distribution. This distribution always looks like this. It never changes. So mu is always 15.4. It does not vary. The population is the population. So the average of these 68 students is always going to be 15.4. But when you start to take different combinations of 10 kids, we're going to get sample values that are different from each other because each set of 10 kids is different. So we take a sample of 10 kids from this population, get 18.1, then get a different value, then get a different value. So we know that X bar does vary. X bar varies. Or the mean of the sample distributions vary. The mean of the sample distributions vary. That is going to show up on your test. Population distribution does not vary. Always will look like this. Samples will vary from sample to sample. The histograms look different. The average value is different because each set of 10 kids is different. Once you have all sets of 10 kids and you graph them, it looks like this. It's the sampling distribution, and it always looks like this. Always. So mu sub x bar does not vary. These are all the possible samples, so that means that mu sub x bar will not vary, and this distribution will always look like this. They each have their own name. Population includes everybody. Samples include groups from the population, but each group is different, so each sample is different. Then you bring it all together for the sampling distribution, which will always look like this, and mu sub x bar does not vary. Okay, so I feel like most of you feel very good about this idea. We have a population, we take some samples, and then we can take these samples and put them down here in the sampling distribution. It gets a little bit muddier when you look at something other than the average. So we had this problem in our notes. I did it with 3B, and I was working my way through it and realized I didn't really understand what this problem was giving me. And by the time I worked it out and explained it to my third period, I felt like nobody understood but me. So I think it's worth going through to verify you guys understand what it looks like when you want to know something like the range or the median, because we're used to seeing average. What happens instead if we want median? So the setup for this is in your notes. This is the Old Faithful geyser. We looked at 1 month of eruptions, and in that 1 month of eruptions, there were 222 eruptions. So we looked at 1 month, and that 1 month had 222 eruptions. And that is graphed here in this histogram. Well, this histogram is definitely not symmetric, definitely not normal. In fact, he's bimodal, and it kind of looks like two separate distributions. On the left, we got this guy, and on the right, we got this guy. So we wouldn't want to know the average of this histogram, because the average would not give us the best information about the eruptions. So what we're looking at instead is the median. And because we're investigating sampling distributions, they just go ahead and give us the true median. So the true median for our population is 200, just kidding, is 75. Okay, well, before we go any further, I guess I better make it clear what we have here. On the bottom it says interval, but what interval really means is the minutes between eruptions. The minutes between eruptions. So we looked at the first eruption of the month goes, then we wait, and the second eruption happens, and we look at the time between those. So maybe it's 20 minutes. Well, actually, it couldn't be. Maybe it's 40 minutes between the first and the second eruption. Maybe it was 70 minutes between the 100th and 101st eruption. What we have graphed here is the time between each eruption. What our samples are then is 10 random eruptions, the time between them. So we had, it looks like, 2 eruptions that were between 50 and 60. So the time between those eruptions was 50 to 60 minutes. We had 2 eruptions that it was 70 to 80, 4 eruptions that it was 80 to 90, and 2 eruptions 90 to 100. So we take one sample of 10 eruptions, and from this sample, the median was 83. Now that's not something that you could calculate. I have to give you the median because histograms don't give you specific values. They just give you ranges of values. But what I now know is that this median is in this bin. It's one of the observations in this bin. So I could highlight that with its own color. Maybe it's this middle observation. Then I take a different sample of 10 eruptions. Notice the sample distribution looks different. They both look similar to the population, especially this guy. But they're different from each other, and they're different from the population. That's because of sampling variability. Well, the sample median of this guy is 72. The sample median, so the middle of this distribution, was an interval of 72 minutes. So the median is 72 minutes between each eruption. So this guy is this bin. So I can give him his own color. Maybe he's this observation. I don't know for sure. I don't know for sure that 83 would be here and 72 would be here. It's okay for me to say, maybe it's this one, maybe it's this one. We just need a concrete example. So, population is 222 eruptions. We take random samples of 10 eruptions and find the median because we want to estimate the median eruption time of the population. Well, we do this a bunch of times and get a sampling distribution. So now this is 500 samples of size 10 eruptions. So in this, our sample of 83 is somewhere in this first bin. Not the first bin, I apologize. It's actually in this last bin. So 83 is in this bin. So this guy is here. And then 72 is somewhere in this bin. It doesn't matter where you put it. It's in the 70 to 72.5 bin. So we took 2 samples from the population, and we could add our 2 samples to the sampling distribution, which I did here. Well, the median of our sample distribution, so this is where things start to get challenging. Our estimate for the population median is the average sample value. So what we do is we add up all of these medians from 500 separate samples. These are the medians from each of those samples. We add them up and divide by 500. That gives us an average sample value of 73.5. This gives us an average sample value of 73.5. This is our estimate of the population median. So this is our average sample value, which is the mean of the sample medians. So we added up all of the 500 sample medians, divide by 500. That gives us our estimate of the population median. So population, we want to estimate the median of the population. So we take samples of size 10 from the population and find the median of those samples, because that's what we're estimating. We take all those medians and plot them in the sampling distribution. Once we do that, we add them all up, divide by 500, and that gives us our estimate of the population. Okay, one more example, and then we're done with the foundation of this unit. So once again, we start with a population distribution. This is the online company that is trying to estimate the range of orders filled in a day. So they look at years worth of orders, years worth of orders. So N is years of data. Let's say years of data. So we're thinking, or I'm thinking, it's 1,000+ days. So the minimum number of orders you filled in those years was 20. The maximum number of orders you filled in those years was 80. The median number of orders filled was 46. They want us to estimate the population range. So that's your max, subtract your min, which is equal to 80 subtract 60. That is 20. We only know the population range so that we can compare it to our estimate that we get from the sampling distribution. This is the population distribution. It's a box plot. Well, now we're taking samples of 40 randomly selected days. So our population is thousands of days, and from that population, we're going to look at sets of 40 days. So what you see on this dot plot is the orders filled for each day. So there was one day where it looks like we filled 23. There were 5 days where we filled 46 orders. But what we care about in our samples is the sample range. So that's our maximum number of orders in the 40 days, subtract our minimum orders in the 40 days. So our max is 74 and our min is 21. So this gives us a range of 53. In this sample, the range of orders filled, the difference between the max and the min is 53. When I plot that with the rest of the samples that I take, this one value is one of these dots. One of these dots at 53. This represents a sample value or a sample that had a range of 53. Okay, here we have a different set of 40 days. Same thing. We want to look at our maximum. Looks like our max is 77 and our minimum of 20. That gives us a range of 57. So this sample range is one of these 57s. I accidentally highlighted 2. My bad. I meant to only highlight 1. So what we see here in this dot plot is 50 samples of 40 randomly selected days. These are our sample ranges. When we say 50 samples, that's the same thing as saying 50 dots. There are 50 dots on this dot plot, and each dot represents a sample range. We got a range of 53 for this sample and a range of 57 for this sample. So our estimate of the population range is the mean of this distribution. Well, to find the mean, we would have to add all 50 of these numbers and divide by 50, which is doable. We could add all these and divide by 50. We could put all 50 in our calculator and use it to find the average. But we get lucky in this case because this is a roughly symmetric distribution. Which means that our median is approximately equal to our mean. So what we are going to use as our estimate of the population range is the median of this distribution, which is 57. So here's how I'm going to write this. The average of the sample ranges is equal to the median of the distribution, which is equal to 57. This is our estimate of the population range. So right here it says our estimate of the population range is 57. Remember, this mu of sample ranges is the same thing as the mean. So once again, I'm going to pull out and do an overall view. We're going to recap and then we're done with this video. We want to estimate something about a population, and typically the population has many more individuals in it than 68. We're talking millions typically, at least thousands. That's an unmanageable population size. So what we can do instead is estimate the value we want to know by taking smaller samples. Well, if we took all the samples that were possible, we could plot them on its own graph, and the average of those samples would be our estimate for the population. So in this case, our estimate, I never filled this in, is equal to 15.4. This is our estimate of true mu. This is the only example where they equaled. My true value is equal to my sample average. It's the same drill for this. We want to estimate the median eruption time. Well, we take a bunch of samples and find their median. We plot all those samples, find their average. That's our estimate. In this case, our estimate did not equal the true value. And lastly, we want to know the range of a population. So we're going to estimate that by taking a bunch of samples of 40 and calculating their ranges. We plot them. Our estimate will be the average of our samples. In this case, it was 57. So once again, doesn't match. I think I did that wrong. I mixed up my numbers. Sorry about that, fam. 80 minus 20 is 60. So we're close in each one, but not equal to. So why do we do all this? Why do we care what the sampling distribution looks like? Well, we care because now that we know this is how sampling distributions work, now that we know we take the samples from the population, if we plotted all the samples, they would be centered at the true value. What we can do then is just take one sample and use it to estimate the population, because we have the understanding that this is how samples work. You take a sample from the population. If certain conditions are met, most of the samples will be equal to or very close to the true value. So this process here, this process in each example, is what tells us I can take one sample from my population and get a pretty good estimate of the true value if some certain conditions are met. And that's what the rest of the chapter or the unit was about. So we had to take a bunch of samples to look at a sampling distribution, because knowing how samples and sampling distributions work enable us to take one sample, not 500, one sample, and be able to answer questions like this. I apologize for this video being so long. If you made it through, you deserve an A+. If you understand this video, I really believe that it helps your understanding overall of this topic, which is not only important to the test that you're about to take, but the next 2 units rely on this idea of a sampling distribution. So the more you understand it, the better. So if you survived, si bueno. What you're supposed to do now is fill out this paper. I put up a completed one so that you had some idea about what to put, but you really should be filling in your own things because this is your study guide. So this is what you do next. You go through and you gather all of the information from our unit onto this one sheet of paper. So the next video you see will be me briefly, I'm talking 15 minutes, hopefully, max, going over this paper. Okay, love you guys.